tonight Rick Mott is going to present to us. Rick and I met actually in Jack Devaney's comments section on his Substack blog, and some of this presentation you'll see tonight is courtesy of some of Jack Devaney's writings and that. So kind of an interesting meeting. We've known each other for about a year now, I guess. And so yeah, just a couple of points here. He'll be presenting on how the current radiation protection standards came to be accepted worldwide, the issues, errors, and head scratching with how we got to this point. Rick will then discuss how radiation protection standards need to be improved, updated, and based on overwhelming scientific data and evidence. Rick is a retired electrical engineer. He spent a career designing software and signal processing electronics for X-ray spectrometry. He has been granted 7 U.S. patents as co-inventor of 5 more. He led the engineering team at Princeton Gamma-Tech, PGT, which received 2 R&D 100 awards in 94 and 96. A PGT gamma detector at a nuclear power plant in Sweden was the first outside the Soviet Union to recognize the Chernobyl reactor accident. This presentation is based on the writings, like I said, of Jack Devaney, including his new book, How We Can Make Nuclear Cheap Again, and various posts from Jack's Substack blog, including the case for 2 millisieverts per day. So before, just one quick point. Maybe you people are all familiar with Dr. Brian Cox from the UK. He's a very good science communicator. And I like this quote he said. I think it, for 2 reasons. I think it applies to tonight's presentation, but also I think to Rick directly. This is what I feel about him. Real scientists are delighted when they find out they are wrong. And to me, that is one of the greatest gifts that a scientific education can bring. There are too many people in this world who want to be right and too few who just want to know. Rick just wants to know, and now he wants us to know. So, Rick, carry on, please.
And besides, you can't throw virtual tomatoes at me through the screen. Won't work. So this is derived. I've been working on this for quite a while. The first version of this talk I gave to my kids' elementary school for the Earth Day after Fukushima. And it was called A Rational Environmentalist's Guide to Nuclear Power. It's grown over the years, and the latest version I gave to an alumni panel presentation at Princeton University last spring. So there will be a lot of material that may be somewhat repetitive for those of you who are already familiar with it. But I'm sort of aiming this at a fairly general audience. There is a lot of detail in the later slides. I won't read them to you, but all of the references are in there, and you can, there's a QR code at the end. You can download a copy for yourself. You're welcome to do so. Okay, so you may be familiar with the concept of peak oil. In 1956, Hubbard put out this diagram where he expected that petroleum was only going to be available on the long term for a fairly short time. And that if we wanted something that was going to last for centuries, we were going to have to convert to nuclear power. And he wasn't all that wrong in the early days. Nuclear power grew fairly rapidly until the Chernobyl accident, at which point it completely flattened out. There have been really no new, except for the last couple of years, there haven't been many nuclear startups in the United States. The existing power plants have generally been uprated. They've been improved. Their capacity has been enlarged, but there haven't been many new ones. He underestimated the demand for electricity that was going to be coming. Even today, the capacity we have is double what Hubbard was predicting for 2060. But this slide isn't completely accurate. If you look at it, it appears that what they call non-hydro renewables, that would be wind and solar, is a really significant fraction. But if you look at the actual generation, you'll find that nuclear is the second biggest contributor after natural gas. And the reason for that is that there's something called capacity factor in the power system. Capacity factor means the ratio of nominal capacity to actual electricity produced. And for wind in 2023, that was about a third. And for solar, it's a bit less than a quarter. What that means, of course, is it takes triple the capacity for wind and 4 times for solar to generate the same usable electricity as a nuclear plant. Now, Chernobyl was actually not the worst accident of power generation in history. This was. This was a hydroelectric dam that failed after a typhoon dropped a huge amount of water, more than 1 meter. And you can't either store or produce large amounts of energy without some degree of risk. When this dam failed, the total casualties approached those from Fukushima, not from Fukushima, from Hiroshima. Just an inland tsunami, massive wall of water. And now, if we look at the Chernobyl, what we find actually is that it was a reactor design that you would never find in the West. It had no containment shell. What actually exploded, it was a steam explosion. The reactor was a repurposed plutonium bomb fuel factory. The design, it was repurposed for civilian power generation. And it had what's called a positive void coefficient. What a void coefficient is if you lose pressure in your water cooling system, you'll get bubbles, you get steam, okay? That will essentially reduce the density of the water. In a conventional Western style reactor, you have a negative void coefficient. If you start to get bubbles, the reaction goes down. This one had a positive void coefficient. When they made the mistake of, this was during a test actually that this accident happened. And what happened was it was tremendously overpowered very, very quickly. And it was a steam blast that destroyed the reactor. But if we look at what, from the historical viewpoint, and we were to attempt to detect the Chernobyl accident statistically in the cancer rates, you would never know it happened. The only statistically detectable cancers were thyroid cancers, and those were because much of the young adult population in the vicinity of Chernobyl was iodine deficient. And so their thyroids basically sucked the stuff up, and they did not distribute it potassium iodide tablets, which is the standard preventative, which was done in Fukushima. The World Health Organization estimated 4,000 excess cancers over 70 years, which is less than 60 a year, in the nearby population. But of course, you'll find outfits like Greenpeace saying that there were, hundreds of thousands of cancer deaths, but you can't see them. So if we want to put that in context, the actual risk over the ensuing 15 years or so was measured, and the risk of contracting thyroid cancer was approximately 1 in 9,000, which is very similar to the annual, without doing any fancy statistics, just taking the number of people dying in car accidents by the population, about the same as the risk of a car accident in the US. But of course, thyroid cancer is largely curable, so relatively few people who contracted it died from it. So why is it that we panicked about this? Well, it's really fear that started in the 1950s, in that period from 1945 to 1963, when there was a lot of atmospheric bomb testing going on. And so people were scared about that. And the movie, we were unlucky in the sense that the movie China Syndrome, which talked about contaminating an area the size of Pennsylvania, was released 12 days before the 3 Mile Island accident, which hurt absolutely nobody. The containment vessel did its job. But still, the news scared the heck out of people. Now, we have to go to your high school chemistry class here and talk a little bit about the chemical elements. Um, they are uh, characterized by a certain number of protons and a corresponding number of electrons in the nucleus, the atomic number. And we don't need to worry about all these details, but it turns out that at the beginning of the Big Bang, uh, there were really only two of them. There were hydrogen and helium, and that's it. All the others were manufactured in supernovas and other cosmic collision events and explosion events over time. So all of the heaviest elements, and by heavy we mean everything up to iron, which is made in the cores of stars, they work for fusion. But iron does not. Iron is a special case. If you try to fuse an iron nucleus, you lose energy. It's already the most stable configuration of all the chemical elements. And so what happens is that the star's core can no longer keep pumping out the heat, which is expanding the rest of the layers into the star we see. The outer parts of the star collapse. There's an enormous rebound explosion, and that blasts all of those elements out into the universe, where they have essentially eventually condense into other stars, like our stars, like our star, which has substantial amounts of the heavier elements in it. And eventually they condense into planets, and eventually those things condense into us. Humans use a remarkable fraction, almost a quarter of the elements in the periodic table, one way or another. Now, you thought hydrogen was just hydrogen because you've always heard it called hydrogen. And I have to confess, I have never heard anyone actually refer to hydrogen as protium, which is the one proton, one electron version. But larger nuclei, any with more than one proton, need neutrons in the nucleus to glue them together. And in fact, the subnucleon particles that keep nuclei together are called gluons. So you can have varying numbers of neutrons in the nucleus, but only certain ratios of neutrons to protons are actually stable. What will happen in, for example, tritium, which is the isotope of hydrogen, which has two neutrons, that is not stable. It will eventually, one of the neutrons will kick out an electron at relativistic speed, that's called a beta ray, and can transform into a proton. So then you have helium-3. The number of nucleons does not change. It's still three of them, and protons and neutrons have very similar masses. But the end resulting nucleus is more stable. It reaches a lower energy state. And so the electron carries away about 18, almost 19 kiloelectron volts of energy. It also emits a neutrino, but we don't worry about the neutrinos much because they can not only go through you, but the planet behind you without noticing. So we won't, many of these nuclear reactions also involve neutrinos, but we're not going to spend any time on that. So that is beta radiation. Another form of nuclear radiation is called alpha radiation, and that's usually the way the heavier elements, like uranium, decay. What happens in alpha decay is that the nucleus kicks out an entire helium-4 nucleus, that is two protons and two neutrons. They have very high energies on the order of 4-ish million electron volts. But they are very heavy, they have a very heavy charge, and they do not penetrate through much matter before being stopped. So you can hold an alpha emitter source in your bare hand. Nothing will happen to you. It won't get through your skin. Now, there's a concept that's going to be important for the rest of our discussion, and it is called half-life. The way nuclear decay actually works is that a measure of the degree of instability of an isotope is how long it lasts, but it does not decay in a straight line, a certain percentage at a time. Instead, what will happen is that in some period that is characteristic for every isotope, exactly half of the atoms of any amount of that material will decay in that time. And then half of that half will decay, and then half of that half of that half, and so on. So it is an exponential declining change in the amount of radioactivity. And activity and half-life are inversely related. So a short half-life isotope is an intense emitter but doesn't last long. A very long half-life, like uranium, uranium-238, the most common isotope of uranium, which is, of course, the most common isotope only because it has such a long half-life. All the shorter half-life atoms of the isotope have mostly declined away. When the Earth formed, there was a lot more U-235, the fissionable material, in our U-238, but most of it's gone. We're down to about 0.3% by this point. So uranium takes 14 decays in order to get down to a stable isotope, which is lead-206 in the bottom there. Carbon-14, of course, is used to measure the age of living things back to about, you can get about maybe 50,000 years out of carbon-14. Beyond that, there's not enough of it left to measure. So you, in fact, are sitting there right now with about 8,000 decays going off in yourself every second. Half of them roughly are from potassium-40, which is called a primordial isotope. That means all of the K40 that's on the planet has been there since the Earth formed. Carbon-14 is made in the atmosphere all the time by the interaction of cosmic rays with the nitrogen in the air. And the reason their activity is roughly similar is because carbon-14 has roughly 1 million times shorter, less material, less atoms of the material in your body. But it also has a 220,000 times shorter half-life. So the potassium and the carbon emit about the same amount. But a small fraction, 11% of the potassium decays, which are ordinarily beta rays, actually kick out what's called a gamma ray. And a gamma ray is what happens when an isotope is formed in an excited state, drops down to the ground state, and kicks out electromagnetic radiation, just like light, just like radio waves, but at shorter wavelengths even than X-rays. And a 1.5 MeV gamma will go, about half of it will make it through 4 centimeters of water, and you're mostly water. So somewhere in the order of a few hundred gamma rays a second escape from you and go visit the person sitting next to you. So why do we care about this? Okay, what ionizing means in terms of radiation is that it has enough energy to break the chemical bonds that make up you, that make up all of the organic molecules. Typically, that's only about 10 eV, 10 electron volts. So these things have enough energy to break those bonds. And damage that happens to our DNA can happen 2 ways. We can directly ionize one of the atoms in the chain itself, or it can ionize water. And ionizing water is actually more common, of course. You are largely water. And what happens when you kick an electron out from a water molecule is you have a free proton, which immediately gloms onto a water molecule and becomes a positively charged hydronium ion. And the OH, that's left, is negatively charged and becomes a hydroxyl radical. And those are called reactive oxygen species. They are very chemically active, and they are what you worry about when you go into the drugstore and you see many, many shelves of the 21st century snake oils called antioxidants. They are supposedly able to prevent the damage from these oxidizing reactive molecules. The damage type we are concerned about is a double strand break in which the DNA, both strands of DNA are split. So the DNA strand is separated into two pieces. And if those are not rejoined correctly, then you might get a mutation, and that potentially results in cancer eventually. So the so-called linear no threshold theory is the fundamental theory that underlies all of nuclear radiation for the last almost 100 years. Back in the 1920s, we are 70 years after Darwin discovered evolution or basically proposed evolution. It was still very much controversial. The Snopes trial happened in 25. And science was still looking for an explanation for how the mutations that go along with evolution could come about. So Hermann Muller had succeeded in causing mutations, he thought, in fruit flies by using massive doses of X-rays. X-rays were discovered in the late 19th century, and people were experimenting with them. Becquerel discovered uranium radioactivity by discovering that film would be exposed by having this rock sit on it. And the experiment was let's use hundreds of thousands of times the amount of radiation that you might ever be exposed to. And yes, indeed, the fruit flies had heritable mutations. And very shortly after that, two famous chemists, Lewis and Olson, proposed that, okay, if a lot of radiation can make mutations quickly, then perhaps the normal background level of radiation over long enough time can also cause mutation. And so almost immediately after that, it was proposed that a single hit statistically could be enough to cause cancer. Mueller got a Nobel Prize in 1946, and there was a genetics panel convened in the 1950s, which decided that the linear threshold model was the way we should treat radiation risk. All radiation is dangerous, which is something that you've probably heard all your life, because it's what's been the accepted model. But it turns out that that's not actually true. But scientific errors can persist for an amazingly long time. You've probably heard of the Feynman quote, that if it disagrees with experiment, it's wrong. And as scientists, we are supposed to immediately accept a result that's contradictory to what we think. When confronted with the book 100 Scientists Against Einstein, Einstein's answer to that was, why so many? If I were wrong, it would only take one. But in fact, science seems to operate more along the lines of Planck's principle. Science advances one funeral at a time. People do not readily change their minds. And I think Planck wins on this one. So this is how the linear no threshold hypothesis, which was unproven. There was no evidence for it, and in fact, there was evidence that already existed against it, because Russell at Oak Ridge was doing experiments with large numbers of mice. And mice, of course, are mammals. Fruit flies diverged from mammals 650 million years ago. So they're quite a bit different. And one of the differences is that mammals, of course, are warm-blooded. And we will be talking about that shortly. But first, let's look at the evidence that linear no threshold can't possibly be right for long-term low levels of exposure. This was a very interesting study that was done in the 90s by a physicist at Pitt, Bernard Cohen, who realized that publicly available data could be used to test the linear no threshold hypothesis. He essentially looked at radon levels, which were published generally by the EPA, over counties nationwide, and public health records could tell him about lung cancer mortality, death records. And he said, well, how are these things correlated? Okay. And so he would plot them after correcting for smoking in particular, but any number of possible confounding factors. And he got an odd result. He looked at the dashed line that goes in the left hand and right hand. The rising dashed line is an LNT slope from a National Academy of Sciences uranium mining study. Basically, he got a lot of pushback, of course. So he did it again with 15 years of data instead of 10 and with a much larger sample size. And not only did he get the same results, he got results that were even stronger. That's a relatively low level of radiation. That's only about, call it 3 times the natural 200 or so millisieverts you get over a 70-year lifetime. So let's look at a more rigorous study that actually does measure the individual doses. There was a study of about 70,000 or so workers on the shipyards that were maintaining the nuclear submarines. And there was an idea that they might be getting high levels of leukemia. There was a report that maybe leukemia could possibly be caused by the radiation from working on the subs. So the DOE funded a big study. That's like 3 times the number of people that you would have in a conventional medical study of actual, medicines. It found something interesting. In the people that were exposed to more than 50 millisieverts over the course of their working career, their all-cause mortality actually went down. It went down significantly. So we don't really quite know what that means, but it might be interesting. Let's look at a little more bit of radiation. There is an area in India where the background radiation is significantly higher than it is here. And the doses that people got were actually measured in people's houses as well as outdoors across the region. The highest dose here is about 7 times the EPA limit for the general public of 5 millisieverts a year. And lo and behold, once again, the actual cancer rates go down. So, what do we want to understand from that? Well, we could understand that at the rate of 40 millisieverts a year, nothing much happens. But there's even better evidence than that. There were a set of apartments buildings built in Taiwan where the steel from which they were made was contaminated with cobalt-60, which is a radioisotope that was used in nuclear medicine in various ways. It is a relatively short half-life, 5 and a bit years, and it is actually the same gamma rays that are emitted by the cobalt that was deposited in the piping of the nuclear power plants of the submarines in the previous slide we saw that showed some benefit. The benefit here is actually quite astonishing. If you look at the table, you find that the number of cancer deaths and the number of congenital malformations, because these were families, they were having kids, were incredibly smaller than what you would expect from the general public. So that says that the cumulative doses, by the way, are extremely large. If you look at the individual doses were up to 4 sieverts, 4,000 millisieverts. Now, all at once, 5 to 8 sieverts will kill about half the people exposed to it. So you're getting up to a dose that if you got it in an hour would not be really good. But over the course of 10, 15 years, maybe it's a different story. So now let's look at a story that everyone knows a bit about, the radium dial painters for luminous watches. These women were studied intensely after it became known that they were at risk of developing cancer, and some of them did. But if you look at the uh, plot in the upper left there, what that is the actual cancers are on the red dots, and the uncertainty boundaries are with the bars, of course. But this is a log-log plot, logarithmic, exponential in both directions. So that means the linear no threshold, which is the red curve, instead of being a straight line, is now an upwards curve. And the cumulative doses here get huge. A cumulative dose of like 7 sieverts or so, gotten all at once, is lethal. The first woman to develop cancer is out here at nearly 10 sieverts of total radiation. Let's see, now is that right? I need to look at this quickly. Yeah, yeah. She was getting a total dose of somewhere on the order of 10 to 25 sieverts of radiation. And only 1 out of 50 women ultimately developed cancer in this group. So all of this adds up to linear no threshold can't possibly be right. If it were, these results would be completely impossible. And this is not subtle. This is not, a 20% effect. This is a 7 times effect. So we need to know why. Here's why. The reason LNT is wrong is because we developed an ability to repair our DNA, and we needed that because our conventional oxygen metabolism damages our DNA all the time. Roughly 50 double strand breaks, which are the ones that we talked about as being the ones that were most likely to cause trouble, happen in every cell of our body every day. And the mechanism is complicated. It's these protein complexes that form to do the repair are large, complex. There were Nobel Prizes awarded 8 years ago for basically explicating these mechanisms. I'm not a biologist. I don't understand them. But it is interesting that even though our senses cannot detect radiation, our cells do. There was experimentation done in the 2010s at the Lawrence Berkeley Laboratory where they irradiated HeLa, that is, those are human cancer cell line cells, with heavy ions. And they looked at the radiation repair complexes appearing and disappearing. These are called radiation-induced foci, RIFs. And they videoed, they tagged them with fluorescent tracers, and they made essentially movies of the development and then dissolution of these radiation-induced foci. The double-strand breaks take the longest to fix. They can take up to 10, 12 hours. But the human cell division time is about a day. So the reason that we have to worry about large immediate doses of radiation is that these protein repair complexes are physically large with regard to the DNA itself. The little gray loop in the lower left image there is the DNA, and the drawings that you see around the edges are the repair complexes. If you get a situation where there are 2 double-strand breaks, a double-strand break, in that length which is enclosed in the DNA repair complex, then the probability of a misrepair goes up very strongly. And so, for example, Rothkamp tested this, and he hit cells with 80 sieverts of X-rays in 3 minutes. He got 50% misrespares. If the same 80 sieverts was given over 2 weeks, there were no measurable errors. So that is an indication that what really should be happening is it should be looking at a probabilistic problem. What are the odds that two double strand breaks happen too close together to increase the risk of causing cancer. So this is something called the birthday problem. It is a combinatoric problem. So if I just ask you, how many people do you think need to be in a room before two of them are likely to have the same birthday with 50% probability? How many people do you need for a 50-50 probability that at least two of the people in the room have the same birthday? Anybody want to make a guess? It's not half a year. It's not 180. It's
32.
About 25 or so.
Very good. Very good. It is 23. That's the magic number. And the reason it's the magic number is because when you have one person, there's 0 chance. When you have two person, there's a 1 in 365 chance. When you have three persons, you have to compare against both of the other two. So it's 1 in 364, and so on. And that is the mathematics of combinatorics, and I would have expected the MIT person to figure this one out. What happens is that you have no probability or very low probability for a while, and then it goes up exponentially. So if we look at the concept that maybe what we should use something that isn't a straight line, there's a good candidate. And Jack Devaney in his books suggests what he calls the 5-parameter logistic curve. Okay, a logistic curve is something that's already used a lot in dose response literature. You want the 5-parameter one because the 5th parameter gets you asymmetry, and the risk curve is highly asymmetric. It starts very low on the scale of the basically 0 to 3 sieverts. That was the results of the studies on the atomic bomb survivors. There was the Radiation Effects Research Foundation in Japan that has been doing work on the survivors basically all their lives. And there have been many, 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 many papers published. The center figure there is various approximations and extensions and fiddles with the linearity of the data at high rates. But when you get down there below half a gray, 500 millisieverts, it's really not really obvious what's going on there. So the blow up at the left is a fit of this 5-parameter logistic function to the bottom 1 sievert of the atomic bomb survivors data, which is the acute exposure, right? And what you would do if you wanted to compute a new risk model is you would take the acute exposure and you would basically look at that at the bottom, the way, way, way bottom end of that curve. And so let's do that. The big curve, let's look at the big curve first. The big curve is, again, log. So there's our linear no threshold line. This is the curve that you get from the 5-parameter logistic curve. It is exponentially declining as we get to very, very low dose. This is the one millisievert down up here in this one. But that's about where the knee of the curve is. It's not very far, but the risk levels are incredibly low. At a single exposure of half a millisievert, the risk is maybe 5 parts in 100 million. Okay, in the LNT at about half. Let's see, where am I looking here? Yeah, at about a tenth of a millisievert. This risk is about 1 in 100,000 for LNT, but it's 1 in 100 million, 3 orders of magnitude lower for the sigmoidal fit to the acute risk curve. So is that plausible? Well, to do that, we have to back up a bit to the Mhm. High background people. Uh, we have maybe about mm, about 13,500 people being followed for 20 years. And that turns out to be on the order of 95 million person days, a continuous exposure throughout their lives of tenth of a millisievert or so, a little bit more. Uh, so that's not completely unreasonable. Now, if we take the SNT sigmoidal curve, which flattens out at the top because there's actually a correction in there on the assumption that cancer can really only kill you once, which is probably pretty close. You find that it is still above zero, but it is significantly above the confidence intervals here. So it's still plenty conservative, but it's not crazy the way linear no threshold is. We want to calculate the lifetime cancer risk. And so we make what's called a dose rate profile. We look at the dose each day, and we then apply all the conversions, all the decays in the activity, and we get what's called a dose rate profile. Integrating the dose rate profile will give us our risk. So if we look at the one woman, the woman with the lowest dose who got cancer, and we look at her cumulative millisieverts, which is like 250,000, her cumulative milligray is like 13,000. And we find that she was exposed for 10, and that's the slow buildup here. She got up to about not quite 17 millisieverts a day. The calculation from SND is she should have had a 60-some% chance of developing cancer, but in fact, it's more like 1 in 50. So SNT is still conservative. It's conservative enough that you could actually consider using it. Let's look at a real accident. Let's look at the Fukushima accident. I wonder what might have been different if the radiation risk assumption had been the sigmoidal curve instead of the linear curve. So in a reactor accident, we are worried about iodine and cesium, both of which have low boiling points and vaporize. So in a meltdown where the reactor vessel is breached, the iodine and cesium will evaporate and they will appear in the plume. But the dose rates are actually pretty low. If you look at the town of Iitate, which is in the upper left-hand part of that red plume in the center there, they were getting on the order of 40 microsieverts an hour, which is about 1 millisievert a day in that area. But the iodine decays very quickly, and something like 90% of the deposited contamination was iodine. So the rate of exposure declines rapidly, and then slowly as the longer half-lived elements start becoming dominant. So we can make a risk calculation. The 1 millisievert per day is an air dose. People don't actually sit next to the outside monitors all day. So we could use about 0.4 of a millisievert a day, look at the declining curve. And what you'll see is that after about 2 months, you are down in the range about 0.11 millisieverts a day after 50 days, which is equivalent to the highest dose, lifetime dose, of the high background region in Canada. So after less than 2 months, they had the same kind of lifetime risk of mortality as the high dose Indian high background group with no excess cancers over 20 years. But nobody was allowed to return to Okuma, which is the county closest to the actual plant, for 8 years. So let's consider another accident that might happen. A standard way of adjusting compensation for an industrial accident, what's called lost life expectancy, okay? You calculate the number of life years that someone has lost, statistically speaking, and you can award compensation based on that. So if we calculate the lost life expectancy for Fukushima under SNT, the worst exposed people, if they did nothing, if they just ignored it and lived their normal lives, no protective efforts at all, they would be talking roughly 2 days of lost life expectancy under SNT. You know, you mask up a little, you're careful not to track stuff indoors, you take a shower, then it'll be less than that. So the total lost life expectancy for Fukushima would be on the order of 2,200 days, 6 years. What really happened? There was a study done by Mr. Oka that looked at the direct deaths from the tsunami and the evacuation, and then the so-called indirect deaths, the deaths that are related, what we would call deaths of despair. Okay, if you look at Fukushima, it had something like 2/3 of the total deaths of people, the older people over 66, in all of Japan. He calculated roughly the lost life expectancy for those 100,000 people evacuated at 5 million days. He thought the evacuation might have saved as many as 2 million lost life expectancy days, according to LNT. But if SNT is right, it's 2,200 days. It's like 2,000 times less. So the evacuation killed people unnecessarily. And actually, if they had known that they could release small amounts of radioactivity without release, there's a good chance the big releases wouldn't have happened at all. Because for Three Mile Island, there's a worry when the core is exposed in a reactor, when the cooling water isn't covering the core, that the zirconium cladding of the fuel rods gets hot enough to split water. It actually grabs oxygen away from the water, generates hydrogen, and hot hydrogen gas is, of course, explosive. At 3 Mile Island, they vented as necessary. They had authority to vent. The maximum exposure was 1 millisievert or so from the radioactive krypton gas that was released, if you were basically leaning on the fence at the boundary of the power plant at the time the venting happened. In Japan, unfortunately, it needed permission from the prime minister to vent the reactor. And the delay was so long that they could no longer get to the vent valve, which was manually operated. The famous explosion that you saw on TV of the first unit actually destroyed the emergency generator that had just been brought in to power water pumping to the 2 other units. So essentially it caused the other 2 explosions that were part of Fukushima. That did not have to happen. So the take-home message from all of this is that not only is the linear no threshold theory wrong, it is so wrong that it creates real panic in a genuine emergency situation. Fukushima was not a very big radiation risk. The thyroid cancer was a non-issue because they distributed potassium iodide tablets to everyone immediately to saturate the thyroid, prevent any kids or young adults from absorbing that. The solution isn't technology because our existing reactor fleet is very, very safe. It's all politics. We need to counter the fear-mongering on the part of some of the more radical green groups. Originally, the Sierra Club on the West Coast favored the Diablo Canyon nuclear power plant, and they did so because they thought it was environmentally preferable to another dam, and they were right. But when the more radical wing of the Sierra Club split off and eventually became part of Greenpeace and the other more, shall we say, dramatic anti-nuclear environmental groups. And those people generate donations and get memberships by misusing the linear no threshold theory to exaggerate risk. And the problem is, it's not just nuclear power that we're worried about here. The EPA now uses the near no threshold hypothesis for all chemical carcinogen risks as well. So we're going nuts trying to mitigate infinitesimal risk, and we really ought to fix that. Thank you.
Very good. Thank you very much, Rick. Very informative. Some maybe some simple questions or summary I would have too. Now, of course, my government in Canada here tells me I'm supposed to be exposed to no more than 1 millisievert per year of radiation. The background radiation here in Winnipeg is 4 millisieverts per year. So I guess.
Do you have lead underwear?
Sorry?
Do you have lead underwear?
Yeah, geez darn, I hope so. Yeah. So, how does this, everybody's accepted this. One thing I am kind of concerned about is, Devaney says this is a plug-in replacement. SNT is a plug-in replacement for LNT. And that potentially could be true, but as we see, there's often bureaucracy and red tape and politics and all that kind of thing. So my fear would be if we did switch, I think that could slow down the rollout of nuclear power because of all the bureaucracy and red tape and things like the NRC, Canadian Nuclear Safety Commission, et cetera. So that's one thing that I'm kind of concerned about. I think a lot of the nuclear reactor companies are okay with kind of making it LNT, but anyway, that's my 2 cents. I think in my view, this is a awareness. Hey, radiation isn't as fearful as we think. Here's all kinds of evidence that shows why, etc. So yeah, that's my 1.5 cents.
Well, in fact, what you really mean is that the existing nuclear power companies have somehow managed to survive despite ankle chains, basically, enormous emergency evacuation plans that they shouldn't do anyway, and like fantastically conservative. Everything has to be nuclear qualified, but nobody makes nuclear qualified stuff, so it's fantastically expensive. Devaney's own company that he was starting in Indonesia, which is Thorcon Power, he was planning to build the reactors using shipbuilding technology, because he was very familiar with that. He was an ocean engineering grad from MIT. And it's not a dissimilar problem. You're under plenty of pressures in those engines, and so it would be safe enough. And the existing people who have suffered under LNT don't want competition from small modular reactors who don't have to deal with it, right? So they're going to not necessarily be on the side of sanity here. They're going to be on the side if everybody else has to wear the same damned ankle chains we had to deal with.
Yeah, okay, very good. All right, very good. Thanks for that, Rick. I'm going to hand it over to Shauna now for any Q&A from anyone else.
Matthew, go ahead.
Hello. So first of all, I made some remarks on chat. You can look them up. But the amazing part is that we get about 10 daily double strand breaks in our DNA in every cell. So each cell gets about 10 of them, which means this is actually the cause of our propensity to get cancer, which is about 1 in 8 in lifetime. And I would like to know, so that's for perspective, right? I would like to know how we proceed, because we don't want to come across as a bunch of zealots who are trying to cram this down the throats of, I don't know, politicians, journalists and whatnot. But I think that this is a sea change, and we need to communicate the sea change. That's all I'm saying. How do we stay away from being zealots yet be effective?
Interesting problem. There is a group called SARI, SARI, Scientists for Accurate Radiation Information. There are maybe 500 people in it. I'm in it. I just joined. And papers have been being published for 20, 25 years. This information is not news. There's a lot of so we say inertia in the scientific community. Um, there's certainly fear by politicians of being the first one to come out with something that goes against everything, right? It's a hard problem, and as I'm saying, it's a politics problem more than it's a science problem. There's tons of science, okay, um, and but we can't get in front of the right set of people to uh, to believe it. I don't quite know how to do that. You're perfectly right. Um, what needs to happen is that we need to get. I think that whatever else you may think about Trump, he is at least looking at nuclear power. He's willing to actually maybe make some changes at the NRC. I don't know who is driving that process, but I think it needs to be. I was thinking that if you need allies in this, the logical place to look for allies is in the health physics community, the people who are doing radiation treatments. You would expect to be the most welcoming to anything that makes people less afraid of receiving them. And that's a relatively large, relatively well-respected entity. But all of those guys have been trained in LNT from the time they first went to school to start learning about health physics. It's an inertia problem. I wish I had an answer.
Thanks. Gary or Jerry, go ahead. I will. There you go.
Yeah, thank you very much, Rick, for the talk. I'm interested about all this subject in different parts of the world. For example, in China, do the same issues apply there?
Oh, I don't think so. I think the Chinese are definitely working on nuclear along with everything else because they are desperate to provide. I mean, they have an enormous, relatively, uh, you know, I won't say poor, but they have a large population that probably doesn't have adequate energy supply outside of the big cities. So they're just building. They're building coal plants like crazy. They're working on building nuclear plants. The South Koreans actually are working a lot in nuclear energy. They're going full bore on that.
Yeah. I think the Chinese too. They have a goal to build 10 gigawatts of nuclear per year. I believe they built 11 last year, so they definitely want to do that.
Yeah, they've started a lot of plants, and they're able to build them much faster.
Mm-hmm.
You know, what we have done in the States, which is probably not too different from what you've done up here in Canada, is there's this thing called the National Environmental Protection. There's some act that was passed in the 70s that enables citizen lawsuits, and that has become a lever. It's become a way to delay projects indefinitely. The first functioning nuclear power plant in the U.S. was about 32 months from first start of construction to selling power. And the new Florida plants, the Vogtle plants, 14 years. Okay, so it's really tough to, and the cost of nuclear, of course, is entirely the cost of capital. The fuel is, relatively speaking, nothing. So the cost of money delayed over time, if you make, if you're calculating your return based on a standard return on investment, stretch the time, and you make the hurdle rate much higher. So delay is a weapon that the environmental groups have learned to use very effectively.
Thank you. Okay, so Leslie had put his question in the text. So he says LNT is appropriate in some areas, for example, lead exposure, smoking, etc. Is there a heuristic that we can determine where LNT is appropriate and where it is not?
Short answer is I don't know. I am not knowledgeable enough on the chemical side to be sure. It's the biological effect is different for heavy metal ingestion, I think, but that's a guess on my part. I don't know enough about chemical carcinogenesis.
Thank you.
So sorry.
Okay, Ray.
Hey, thank you for your talk. I don't have a question. I've just got a couple observations. It seems to me that the LNT regulation is directly responsible for the 8 to 9 million deaths per year from fossil fuel pollution, because if we didn't have LNT, we would have nuclear energy and not fossil fuels at this point. So LNT is also responsible for our climate change problem.
Actually, there's another slide that I didn't put into this presentation that I did for when I did the first version of this talk for the elementary school. And what that talked about was the particulate pollution for the small particulate pollution, the PM 2.5 from coal plants. And the coal plants I live on the East Coast, right? All those coal plants in Ohio are upwind of me. And my line in the slide was, talk to me about the dangers of nuclear power after the coal plants upwind of me are all gone.
Yeah, and then one other thing is that Trump may be doing some good with getting rid of the
You're breaking up.
Science and political nuclear regulation we've had. But there's a lot of people that are changing their opinion, and I see that accelerating as well. I also see companies that are scaling up to make one nuclear reactor per day, like Copenhagen Atomics.
That'd be great. I hope it happens. I mean, basically, the reason Devaney started as a company in Indonesia is he thought it was just impossible in the U.S. So we can hope that things change. If you want to, you were worried about looking like crazy people. If you want to look like really crazy people, who are also probably correct, a fair fraction of the SARI membership buys into the hormesis hypothesis for radiation, which is what is hinted at by the Taiwan, actually pretty damn strongly hinted at by the Taiwan results, which is that small amounts of radiation are actually beneficial. I haven't seen yet. I've tried to get the paper from the guy who told me about it. There was apparently an experiment done where they took mice and they shielded them from all radiation. They not only, they put them in a salt mine, so there was no cosmic radiation. Somehow or other, they managed to strip the K40 and the carbon-14 out of what they were feeding them. And when they did that, the young mice didn't develop immune systems at all. So there's a possibility that we evolved to use background radiation as a trigger for the development of our of certain parts of our metabolism, which is a strange thought.
There's also a book called Underexposed: What If Radiation is Actually Good for Us? It should be low dose radiation, but I read that book. It was published in 2013, and there's some compelling evidence in there, I feel. And some of us Canadians may know Dr. Joe Schwartz, Office of Science and Society at McGill University, received the Order of Canada. He told me, and he agrees with hormesis himself. So.
Yeah. So I want you to try to imagine convincing the FDA to come up with a recommended daily allowance of cobalt-57 gamma rays. Everybody should stick one to the ceiling in their bedroom, right?
I'm going to go hug my granite countertops now.
My solution to this is I like to collect uranium minerals because they are wonderfully fluorescent. They fluoresce a nice bright green. And I just open the mineral cabinet and take a sniff a couple of times a day.
Sure, just a quick one. Is this what you were referring to?
Yeah, that's the hot plate. Yes, that's the old Vaseline glass. Yep.
Is there? Yeah. This is made like in the 1920s or something. Got it at a antique store here for $15 a few weeks ago. I got a radiation detector. It's almost 3 times what the background radiation is here.
Well, so, I'll tell you what I have is a Fiestaware plate. The orange Fiestaware that was made again prior to World War II used a uranium glaze to get this nice bright orange. And that baby, if you have a Geiger counter which is sensitive to alphas, you need what's called a mica window, a pancake detector with a mica window. I have one that's about 2 and change inches in diameter. That baby will light up with about 20,000 counts a minute.
So here's the thing. There is one more obstacle, which is that right now in the nuclear industry and any job really that requires contact with nuclear sources, and that's my experience, basically they measure your radiation dose over a quarter, and then they send the dosimeter to check. So you could technically get the whole allotted, 50 millisieverts per year in one day, and that would still technically be fine. But that 50 millisieverts is 25 times what Jack Devaney thinks is an appropriate daily dose of no concern. If the industry were to switch to the sigmoid model, then they would have to measure the dose daily and record it daily. In fact, Jack Devaney is complaining many times that he is not able to get the actual dose profile day to day because it is company secret. So that's one reason to worry about let's say, status quo having to be moved. All right, that's all.
Okay, that's a reasonable argument. I would think that, you would, how would you do that? You would basically, dosimeters can be read. So are you using the typical dosimeter is now not a film badge anymore. I'm old time. There's another technology and I'm blanking on what it's called. Can you read it out easily? Yeah, shouldn't be that hard. I mean, you don't need to do it daily, weekly, monthly, probably okay. Tough problem.
So Michael has put his question in text, and his question is, do the Chinese reject the LNT model?
I don't know. That is a good question. They may not be worrying about it quite the way we are. Well, the problem is the reason it's hard to tell is that the process by which regulation decisions are made is pretty opaque. I don't know if it's publicly available or not. I'm not aware of any information.
Okay, that's great, Rick. We really appreciate your presentation here. Very informative. That's good.